Okay, so let's start again with our basic task. We have seen that we are able now to compute the direct kinematics of arbitrary manipulators, provided that they are open kinematic chains. Now we will address the inverse problem. So what is the inverse kinematic problem? In the classical sense is give me a desired pose, so end effector for the end effector, so position and orientation of the end effector. Find some values of the joint variable which will realize that pose. How many solutions? Well, I don't know yet. If there is a solution, none, multiple, infinite, whatever. Okay? So this way, this is a so-called synthesis problem. While the direct kinematic is just analyzing things and describing correctly things, so setting the frame in a appropriate way, associating to them parameters, evaluating the Denavit and Artenberg transformation matrices, doing the products, and that was it. Okay, so there are choices to make, but it's very systematic and there is no problematic of finding a solution or no, or something like this. While here we have to synthesize a solution, so to find solution to the problem. And typically the classical data are a desired pose, so a transformation matrix, numbers, with a rotation matrix and a desired position for the end effector. Remember, we shortly say for the end effector, but this is the desired position for the origin of the frame attached to the end effector. Okay? And this is the desired orientation of the frame attached to the end effector. So the nth frame in a Denavit-Artenberg convention, or also the end effector frame which is roto-translated by a constant matrix with respect to the last frame. You remember we generalized this. So if the input data are given in this form, this is, I would say, I call it, it's not standard, classical formulation. The inverse kinematics for a given end effector pose. But now, since we have introduced the direct kinematic as a more general concept with a vector function of the joint coordinate producing some task variable, and this task variable may be an extraction of those coming from the pose of the end effector, but may contain whatever we need. So we can also use this formulation. So we have an desired R vector, task vector. For instance, taking out of that position of the end effector and triangle which represent the orientation desired for the end effector. Or maybe other value depending on the task kinematics that we are using. Remember, R equal F of Q, whatever it is. It may contain the position or the height of the elbow. It may contain whatever other kinematic information. And then the problem is the inverse. So given the desired value of the task, find a set of value of the joint variable that we realize that value. Okay, so this I call it generalized formulation. But the problem is the same. It just depends on how you handle things. Why is the same? Because in both cases, it's a typical nonlinear problem. We like nonlinear problems. It's not that it's a nonlinear problem, so, oh, what a mess. No, most of the problems are nonlinear. But which means when you try to solve some set of equation, that you have to answer to these three questions. First, existence of a solution, because there's no guarantee that, no easy way to guarantee that a solution exists. But we will see that since these are robots, this is related to the definition of the workspace. Okay? Second, when a solution exists, is it unique? Are there multiple solutions? How many? Or are there infinite solutions in certain cases? An infinite number of solutions, okay? And finally, once we have commented on this aspect, which are still of an analysis, but which are maybe preliminary, especially the workspace definition, to the fact that we have to find one of these solutions, how we do this. So what are the solution methods? Okay, so we will go through this step by step. So this is an additional slide that I put just from the KUKA website, just to say, okay, but what are we looking for? So this is a generic. It's not the lightweight robot because it's a 6R robot. In fact, it's the lightweight robot where you're frozen joint 4. Okay, so here, in general, there is another joint, but here is just eliminated graphically. Okay. So the direct kinematics would be, I give some joint values to the angle, and the angle, remember, defined with some convention. So, for instance, the Dynamic-Tartenberg convention. And then through the direct kinematics, I compute position of the origins of this frame, and orientation. Here they are using roll pitch yaw of this frame with respect to the base frame. And here you have the transformation T06, the sixth frame with respect to the base frame. Okay. The inverse kinematics is, I give you these numbers, and I would like to find those numbers. Okay. Do you think that if I give these numbers, I will find always those? I haven't heard. Go. Not? It's not guaranteed. It's not guaranteed. Because depending on how you compute this, you may find another solution. Okay, which when inserted in the direct kinematics will provide this. Okay, so there are multiple configurations in general that gives the same pose of the end effector. So when we are trying to solve the inverse problem, we should be aware of this possibility. And if we want to solve this problem analytically, which means writing the solution in terms of the data with functions, then we have to insert in this solution options in order to get one solution or the other solution or the other. Like we did when solving the inverse representation problem with a rotation matrix, find the sequence of 3 Euler angles. There we have found one angle, and then depending on cases, we have found an infinite number of solutions, or in the generic case, 2 different solutions when extracting a square root of a number and then carrying over a plus or minus sign, and this generates 2 solutions. Okay? Same thing here, only that the other solution will not be so simple, so a plus or a minus. They will really be completely different in general. Okay? So, solvability. So first of all, if I give you a pose which is on the moon, there is no solution for my Earth-based manipulator. Okay? Why? Because this is out of the workspace. Intuitively, it's clear what we mean, but in fact, this is a very delicate subject, and I've tried to specify it better, but I would need to enter into different kinematic aspects that are beyond the scope of this course. So, but essentially, we define, usually robotics is defined, 2 types of workspaces. The so-called primary workspace, WS1, which is, pay attention, the set, now we refer to the classical inverse kinematic problem. So, given a pose, find joint values. So this is the set of all the position of the origin of the end effector, okay, of the frame of the end effector, that can be reached, so realized, with at least one orientation. So I don't care about the orientation. I just care about positioning the end effector. Okay? All these points in the Cartesian space describe the primary workspace. Of course, if I give you a point P, which is outside the primary workspace, there will be no solution to the inverse kinematic problem at all. if I give you a point inside the workspace, primary workspace, then there may or may not be a solution depending on which orientation I would like to have. Not all points inside the primary workspace can be reached with any orientation of those that the robot can realize. Okay? And we will make a couple of examples later on. So this is why, but of course, since by definition, there is some orientation given by R or the vector phi of three angles, such that I have a complete inverse kinematic solution when the position is inside the primary workspace. No? Because by definition, there is at least one. Now, if I'm giving exactly this solution, this desired value for the orientation, I will find the solution. But I'm no guarantee to find for other possible orientation. So this is why somebody introduced the secondary workspace, WS2, or also called dexterous, which is, in fact, a subset of the primary workspace in general, which is the set of all Cartesian position P that can be reached, so they are certainly in the primary workspace, but at which I could realize any desired orientation, any. And already at this level, saying any should be specified further. Because if, for instance, the robot is a planar robot, so its orientation can only be an angle with respect to an axis which is normal to the plane. And if I'm asking to go out of plane, I will never have this possibility. But in that case, I should think, okay, this is a planar robot. It can have only orientation around one axis. So I can define a point in its secondary workspace if I realize in that point any of this orientation around the normal. Okay, not those that the robot can anyway not realize. So while my words can be relatively clear, I hope, you can imagine that formalizing this mathematically is not at all a trivial problem. Okay, this is why we're just being a bit fuzzy on this and just work on some simple example to understand the concept. Okay? For instance, here is what you typically find in the data sheet of a manipulator. And this, for the time being, let's consider this to be the primary workspace. So we are only interested in the position of, let's say, the center of the wrist of this robot. By the way, this Fanuc, I think it has a spherical wrist, so we're interested in positioning of this point here. Okay. Now, the workspace is, how do I build the workspace? Well, this is from the drawing of the designer of this robot, but essentially I can fix θ1, so the base angle here. So I have a plane, and then I move the second and third joint in this plane, and all the position reached by the center of the wrist will be part of the primary workspace, by construction, I would say. Okay? Now, why did I froze the first joint? Just because there is an axis of symmetry. So if I take this plane, or this area in the plane, and now I rotate the first joint, I will describe a solid object, which is the primary workspace in 3D. Okay? This is why you typically see in those pictures a side view, a top view, or whatever, in order to have enough information, geometric information, for deciding where the end effector can go. Now, if you imagine that this spherical wrist has no limits for any of the three joints, then this primary workspace is also the secondary workspace. Because in every point that I can reach in position, I can assume any orientation using the last three joints. But this is not the case, because these three joints, for instance, I'm sure that I can rotate the last joint 360 degrees. I may also rotate this joint by 360 degrees, but the fifth joint, which is this one, has typically a limit. So I cannot go in any configuration, but just for the purpose of realizing. So this is a typical workspace. Now, let's go back to our good old friends, the planar to our arm. It seems silly, but many concepts can be described on this arm, even if you never encounter this arm in reality or in application. Okay? So we have built for that the direct kinematics. Remember, for solving the inverse kinematic, you have to start with an expression of the direct kinematics. Okay, if you want to solve it analytically. Okay, so let's compute the workspace for this robot. And suppose, for generality, that the two link lengths, L1 and L2, are in general different. So, first case, L1 is different from L2. Now, what are all the points that can be reached by the center of the gripper in the plane? Well, I stretch the arm, then I can move along the radial axis toward the center until I fold the arm. So I'm describing, for instance, I stretched here and then I'm describing this set of points. I'm folding the arm along a radius that goes through the origin. And of course I cannot reach the origin in general because the two link lengths are different. Okay, so when I completely fold it, I have still a hole here. And this happens no matter if L1 is longer than L2 or if L2 is longer than L1. You see it? Okay? Suppose that this last link is very long. You will have a situation like this. Now, this is when the robot is stretched. When I'm folding it, I'm going here. So this part cannot be accessed. So it's the difference that matters, the absolute value of the difference of the link length. Now I'm moving the first joint and the third joint rotates. So from this segment, what comes out is a sector. How do you call it? I mean, this a circle with a hole inside. Okay. Which is funny because you think that when you're close to the base you can do whatever you want. In fact, you cannot. And it's not so strange because this is exactly what happened even here. You have a hole inside. Pay attention. Here the hole is also due to the fact that these joints, 2 and 3, have a limited joint range. In our next case here, we haven't assumed any limit for the two joints. They can rotate freely 360 degrees. If we put some limits, then some part of this area will be gone. Okay? And you can see also on the book some example of the funny aspect of this workspace, even in this very simple case. Now, we can give an analytic expression to the primary workspace, which is all points in R2 whose norm is between the absolute value of the difference of the link lengths and the sum of the link lengths. Okay? Secondary workspace. Well, it should be some points inside this area. But here I realize that when I look at the orientation, now this is a planar robot, so the only orientation that I can have is an angle, let's say, with respect to the x-axis. Okay? So I can have one orientation or the other, but always in the plane. Now look here. If I'm at the external boundary of the primary workspace, I can only have one orientation. I cannot go like this, because if I go like this, I leave the boundary. I'm entering the workspace. Okay? Similarly, in the inner boundary, I have again only one orientation. In between, in any point inside the primary workspace, I can be there in two possible configurations of the robot, which we may call, say, the right arm or the left arm, okay? And so we have only two possible orientation, depending on which of this inverse solution for positioning only we are choosing. So in every case, I have either one possible orientation or two, but not infinite. So the secondary workspace is empty in this case. Okay? No wonder if you take the two links of equal length, so L1 is equal to L2, let's say calligraphic L. So what happens to the primary workspace? This boils down to 0, and this becomes 2L. So you're saying that so the whole vanishes. The whole vanishes. But something else happens, because now the origin of the workspace, of the reference frame, so XY, so when the arm is completely folded, it's just a particular position in the primary workspace. Actually, it's the center of the primary workspace. But it's also the only point which is inside the secondary workspace. Why? Because when I'm folded like this, let's do a drawing, when the two link lengths are of equal length, I'm folding like this, and now when I rotate the first joint and leave at 180 degrees the second, I'm realizing for the end effector any orientation. So this gripper is pointing now in this direction, but can point there if I move like this, and so on and so on. So any of the feasible orientation. So this single point belongs to the secondary workspace. Okay, it's a simple example, but I hope that you start realizing the differences. Okay, now look at this other case in terms of number of solutions. We have seen, by the way, that in the previous case, when we are assigning the position inside the primary workspace for a generic length of the link, so means L1 different from L2, then we typically have two solutions, left or right arm. At the boundary, we have only one solution. And if the link lengths are equal, at the center of the primary workspace, which is also the secondary workspace, the only point, there we have infinite solution, because we have folded the second link, so we have 180 degrees for theta 2, but then any value of theta 1 will leave the end effector at the desired position. Okay, so you have seen that even in that case, we have a multitude of inverse kinematic solutions. What about a spatial arm, actually an industrial arm? This is just a sketch of the Unimation Puma 560. So articulated robot with 6 revolute joints with a shoulder offset, an elbow offset, and a spherical wrist. This is how you qualify this type of robot. Now, if you forget about the last 3 joints, the last 3 joints are this rotation, and then the final rotation of the flange, which is not shown here. So you've frozen this. And in fact, you don't care at all about this, but you care only about the positioning of the center of the wrist, which is more or less here. So you're using only the first 3 joints, theta 1, theta 2, and theta 3. Now, if I'm inside the primary workspace, then I typically will have 4 inverse kinematic solutions. And here are shown for a generic position. And they are, in fact, one with elbow down. Now I extend the arm. Now I do something that I cannot do otherwise. And come like this, and this is elbow up solution. Okay? I have to do this rotation because my elbow has a limited range. Okay, so these are the two, elbow down and where is it? Down and up. But then there's is the way you want to label, left or right condition, which means I could do like this, elbow down, right, but I could do also elbow down, left. See, but I have either the right or the left hand, no? But in fact, this configuration is the one that I realized by rotating like this, going up like this, and then reversing and doing this operation, okay? Again, if I had the elbow up, then I rotate, I go down, elbow up, but this is a different configuration. So one is facing the point and one is having it on the back of the robot. Okay? So these are the four solutions for positioning the wrist center only. So for a sub-inverse kinematic problem, you see that the concept of having a vector R specifying the task is very useful because I'm saying I'm interested only in that part, not in position and orientation. Or I'm interested in everything. For instance, if I'm interested in positioning and orientation, then the solution becomes 8 for this robot manipulator. Why 8? Can you imagine why they double? And what they don't become, I don't know, 32 or 3 times 4, I don't know. Why they just double? Remember, this is a spherical wrist. Huh?
Because I have other 3 joints.
I have other 3 joints, so?
It's like the situation. It doesn't double the
Why with 3 joints, I have 3 additional joints, I have double the number, and if I had only 2 additional joints, what would be? So, the point is that, again, suppose that there is no joint limits. Now, and forget about the first 3. So I have only the wrist now, which has 3 possible rotation around the joint axis 4, joint axis 5, and joint axis 6. And these axes are all incident to the same point because this is a spherical wrist. So the axes always intersect. So these 3 joints, variable, theta 4, theta 5, and theta 6, are in fact a sequence of Euler angles. Because theta 4 is the first rotation around some axis, actually a z-axis, because then Q5 will be a rotation around the local z-axis, but after the previous rotation, because it's an open kinematic chain. So it's an angle defined around the moving axis, because the z-axis of joint 5 has been moved by the rotation of joint 4. Okay? And finally, Q6 or theta 6 is the third angle around an axis, current axis, a z-axis, which is the result of the rotation of the previous one. So in fact, Q4, Q5, and Q6 as such characterize a sequence of Euler angles. So what? Now we know that if we give values to this, we have an orientation, R. Now the problem is, give me an orientation, R, for the end effector of the robot, realize it with these 3 angles of the spherical wrist. So it's the inverse representation problem of orientation that we have already found, and in general, out of singularities, out of cases which should be handled differently, we have 2 solutions. So if now we mount the wrist at the end of the first 3 links, for each solution that positions the center of wrist, one of these 4, we will have 2 solutions for orienting as desired the end effector. So for each one we have 2, we have 4 base solution for the main 3 links, and then we double. Okay? But this is a special case. Pay attention. This is a special case. By the way, if you want to really look at how this looks like, here I found this additional slide. So these are the 4 inverse kinematic solutions for positioning the center of the wrist. Okay? Now, for each of these, there is, I hope I made the association well, there are 2 possible solutions for the last 3 joints. And now look at how this coding, black or white, is made. For instance, look at this one, or maybe this one. This is the first joint, and this is the back of the first joint, of the first link, if you want. Second joint, third joint, so this is elbow down. Now, these 3 are the 3 axes of the wrist. And you see that this is top, then there's something, and this is down. Okay? And here, same solution for the first 3 joints, and this is down, this is the same, and this is top. It's just a matter of coding. Okay? So these are the 2 solutions for the wrist associated to the, let's say, left elbow down solution. If you take the right elbow up, again, see, you have why these are different, because these are facing the desired position. These have the bottom or the back in the direction of the end effector position. So they have had a rotation of 180 degrees or similar. Okay? And again, this qualifies the base, and then the elbow up are the first 2 bolts, and then you see again a combination below, below, and up, up of the joint 4 and 6 for the orientation. It's just, I mean, there should be numbers there, but it's just a representation, a schematic representation to understand that why these are different. If you look at them, they look almost the same, but then you should realize that the joint variable of the spherical wrist assume complementary angles. Okay? So we have seen an example. Now let's summarize here. For the positioning of only the positioning of the end effector of a planar 2R robot, how many inverse kinematic solutions did we find? Well, inside the primary workspace, always 2 solutions, no matter if the link length are equal or different. On the boundary, we have found 1 solution. And pay attention, if the link lengths are equal, the internal boundary vanishes. So there's only the outer boundary. And there, I need to put the arm stretch, and there's only 1 solution. Okay? Now, only in the case where L1 is equal to L2, and I'm assigning a desired position in the secondary workspace, which is just 1 point, so I'm assigning the origin as desired target position for the end effector, I have infinite solution because I have infinite values for the θ1 variable that realize the same position, while θ2 should be folded by 180 degrees. Okay? Then we call, for the time being, bear with me, those type of solution singular, while the 2 number of solution will be the regular case. Because if I'm taking a desired position inside the primary workspace, and if I take this position out of a bag without looking at the numbers, typically I will be inside the primary workspace, because the boundary is a set of measures 0, so the probability that I'm taking a point on the boundary is practically 0. So the regular case will generate 2 solutions to the inverse kinematic problem. But those special cases are called singular because the number of solutions is different from the regular one, either 1 or infinite. Well, you could call singular also the case where there is no solution because I'm giving a point outside the primary workspace. But this is not of interest. There's no solution. Full stop. Okay? Now, the reason why they are called singular will be clearer when we do differential kinematics, because we associate to the mobility of these robots, so to the velocity that they realize when you give velocity to the joints, a matrix which is called the Jacobian. And there are configurations exactly when you have a number of solutions which is different from the regular one. In that configuration, the Jacobian becomes a singular matrix. And this is why those configurations are called singular, and singular solution when you're trying to solve with this configuration some inverse kinematic problem. Then for the positioning of an articulated elbow type 3R robot arm, like the first three joints of the Unimation Puma, or the first three joints of the KUKA KR5 that we have in the lab and that you will see during the visit, we have four regular solutions. Pay attention, we take the singular case out of consideration here. But there are singularity also in that cases, where either you have a reduced number of solutions or you have infinite solution. You can imagine that when I stretch the arm like this, for the just positioning, and I have three joints like for the UNAP, how many inverse kinematic solutions are there? When I need to stretch my arm and forearm. One or two? I've heard both. In general, two, because I have this solution and then rotate and extend, and I have the other solution. It's just the elbow down, elbow up that collapse into one. Okay? Suppose that you have no offset of the shoulder or of the elbow, and the desired position is exactly on top of the first axis. How many solutions do you have? Oh, remember that I cannot go like this. This should remain in a plane. And I'm bringing this on top at the desired height. How many solutions do I have? Two. Because if I rotate, the position will not change. So if I'm only interested in end effector position of an articulated elbow type arm, I may also have an infinite number of solutions. In this case, theta 1, okay? Then it could be twice, not infinite to the 2, but 2 infinite, because I could have elbow in one sense or the other for the second joint variable. But this is another story, okay? Or for the third joint variable, sorry. Okay? So you see that all these cases may happen. So now, people have investigated the most general case where it makes sense to count inverse kinematic solution. Remember that if you have prismatic joints, then things are easier, because prismatic joints have not this symmetry of trigonometric equation where the cosine of an angle is equal to the cosine of the opposite angle so that you can generate the same number. So in prismatic joints, you have, in general, a lower number of solutions to the inverse kinematic problem. So the most difficult case is all revolute joints. Why 6? Because if you go beyond 6, like for the KUKA lightweight that we have in the lab, so 7R robot, and we are trying to solve the problem of given a position and an orientation for the end effector, which is a task defined by 6 variables, and I have 7 variables to choose, just this counting will suggest that there are an infinite number of solutions. So counting regular inverse kinematic solution makes sense up to a robot with 6R. Okay? So the 6R robot is the toughest robot for which you may look for an inverse kinematic solution, possibly in closed analytic form, and you want to count the number of distinct solutions. Remember, you should remove the singular case, because if you are in a configuration which is singular, then you have an infinite number. Only when you are in a regular condition, you have possibly a finite number of solutions. So how many inverse kinematic solutions are there? We have seen some examples, the Unimation, where the inverse kinematic solution were 8. But this is a special case. How do you put an upper bound to this? The idea comes from this consideration, so that when you look at those set of nonlinear equations of the trigonometric type, in fact you can introduce some algebraic transformation and transform equations into a single polynomial equation. For instance, I have here an example to understand how do this algebraic transformation work. Suppose that you want to solve this equation. A sine of theta plus b cosine of theta equals c. This is non-polynomial in theta, is transcendental. Okay? So I cannot say if there is a solution or not depending on the value of a, b, and c, and so on. Okay? But can I transform this into a polynomial equation? Question. Yes. How do I do it? I have here the solution, so for me it's easy. Well, the transformation in this case works as follows. You introduce a variable u, which is just the tangent of the half angle. Seems strange, no? So every time you find the theta, you should replace it using this transformation. But actually, I need to invert this transformation. Okay, and the inverse, since I have sine and cosine here, is giving, I'm writing the inverse directly in terms of sine and cosine. And these are as follows. Sine is 2u over 1 over u square, and cosine is 1 minus u square, 1 plus u square. Okay? So these are, in fact, the inverse of that. If you want to, you can make the arctangent of this and then have an expression of theta as a function of u. Okay? Do you believe that this is the... First of all, you see that if you square and sum, you have 1 here, after simplification. And also, in order to get those expressions, you should... so, for instance, this says that tan of theta, so doing the ratio, is 2u over 1 minus u squared. Correct? Now, tangent of theta over 2, you can... better say here. This tangent can be written as tangent of 2 times theta over 2. Okay? It's just a trick. So I'm doubling the half angle. But now I use the duplication formula for the double of an angle. So for instance, sine of 2 theta, you know that is 2 times sine cosine of the angle. And there are similar formula for the duplication of this, and I have the expression here. This is just 2 times tangent of theta over 2 divided by 1 minus tangent square of theta over 2. Okay, and if you look at this, you see that this 2u and 1 minus u square. So there's you have imposed 2 conditions. So this is really the inverse of that. Now let's cancel this and just keep this expression. And now we use this algebraic transformation to replace it into the original formula. And we have A times 2 times u divided by 1 plus u squared plus b times u minus u squared divided 1 plus u squared equals c. And now you multiply by u plus 1 squared, so you have u plus 1 squared here, and this is gone. And now you reorder things as power of u. So you have, first of all, you see that this is a polynomial equation in u. And if you reorder things, this can be written as, so you bring u to the other side, you have b plus c u squared, so from here and from here brought to the other side. Then you have minus 2a times u brought to the other side, and then you have plus c minus b equals 0. The second order polynomial, you can find in closed form the two solutions, u1 and u2, and depending on the parameter ABC of this equation. So you can see that this equation has at most two solutions, because we have transformed it into a polynomial equation of degree 2. So there cannot be more than two solutions. Why I say that it at most two solutions and not two solutions? Because when I find my solution here, u can be complex or real. And if it's complex, I cannot put it here, because this should be a real number. So in that case means that there is no solution for the given ABC. So looking at the polynomial equation tells you everything. Using the powerful algebraic results on polynomial equations. So there is an upper bound on the number of solutions. Now, with this in mind, people doing research in kinematics have dealt with this problem for years. There was one guy that said, okay, I was able to find a much more complex transformation, but of this nature, and was able to transform the general direct kinematic problem into a single equation of degree 128. So he could conclude, in general, there are no more than 128 solutions to the inverse kinematic problem. Some smarter guys made different transformation and brought back the degree to 64, and some other to 32. And finally, somebody says, no, with this transformation, I'm able to represent any 6R robot, the problem of solving the inverse kinematic, into a single equation of degree 16. Okay? And then there's a guy whose name is Mansur, who showed one robot, not very complex, with some twist angle, but not very, that in a certain position and orientation had 16 distinct inverse kinematic solutions, all of them non-singular. So he said, there's no sense in trying to see if this number can be reduced, because I have already found one case where there are 16 distinct solutions. Okay? So the Unimation Puma is yet another special case where there are only 8 inverse kinematic solutions, but this is, again, a special case. In general, you say that there cannot be less than 16, more than 16, but if they are 16 or 8 or less, this depends on the specific robot. Okay? So this is a long story, but it's a very interesting scientific story, because it's using a purely mathematical trick in order to fix the upper bound to the number of solutions of nonlinear transcendental equation. Okay, now let's do another example to generalize things. So I've mentioned that in terms of numbers of solutions, if I go beyond 6R, for the general case, I will be redundant, so the number of solutions will be infinite anyway. So let's make an example which is simpler. So consider only the positioning of the end effector of the robot in the plane, where we know we need just two task variables to characterize the position of the end effector in the plane. And in fact, if we have a 2R robot, we find that in general we have a finite number of solutions, which is 2, except in singular cases, 0 if I'm out of the workspace, 1 if I'm on the boundary, infinite if the link lengths are equal and I'm specifying the desired position at the origin. What about this case? So I have a 3-link planar arm, and I'm interested in solving the inverse kinematics. So in order to check the number of solutions, I have to describe its workspace. So I try to see what is the workspace, primary and secondary. Okay? And now look, even in this simple case, how things branch out in multiple possibilities. So first of all, in order to make things simpler, but I suggest to you to analyze the more general case, suppose that the 3 links have equal length. So let's say calligraphic L. So what is the primary workspace? Well, the primary workspace is a circle of radius 3L. So there is no hole at all inside. So I'm stretching things, and this is 3L, and then any other position can be realized possibly in many ways, but then the associated end effector position belongs to the end effect to the primary workspace. But look at this. This is very nice. So in this case, I have, and I need a drawing here. So if you're close enough to the base of the robot, so here you have a 1, 2, and 3 of equal length. Now here there's a 3L is the outer boundary. And now I'm saying that if the position is inside a radius which is equal to the first link length, so inside this box or circle, I can put the end effector in any possible orientation for the in terms of planar orientation. And you can do this very simple. Take any point here. Remember that this is the length of the link. Any point, and then decide what is your desired orientation. Do you want to point up, for instance? You want to look here. This means that the third link should go like this. Okay? And now, with the first 2 links, I just have to reach this position. And I can do this in general with 2 different solutions. Okay? So no matter how you pick a point inside a circle of, or even at the boundary of a circle of radius L, you can then choose any orientation in the plane and then go at the base of the third link and place the first and second link so that the tip of the second link is at the base of the third. And you can do this in general in 2 things. Why this is limited here? If I'm taking a point here and I'm saying that I want to point in this direction so that this goes there, this is the third link. Now with the 2 links I cannot reach this point. So here I can reach this position, and possibly with many configurations like this one. But if I'm choosing any orientation in particular, this is which is the worst case, this point is out of the workspace of the 2-link subarm, so I cannot reach it. And so this is not feasible, and so this defines the secondary workspace for this robot. Okay? Now, having clarified primary and secondary workspace, let's count the inverse kinematic solution. So if I'm in the primary workspace, except the following one, then I have infinite to the 1 regular solution. Infinite to the 1 means that there is a continuum of solution. For instance, here, I'm somewhere, let's say, between these 2 points in the, let's say, in this area. And then I place the end effector and I have some orientation. Then I can change the orientation for a while. I cannot assume any orientation because as soon as I go out of this or below this, the first 2 links are not sufficient to reach the base of the third link itself. Okay? So I have all this solution for the third joint angle, and associated to this I have typically 2, but in this limit condition only 1 solution for the first and second joint. Okay? So I have infinite to the 1 solution, which is what I expect. This is a redundant robot. 3 joints, 2 tasks. So I have, in general, so the generic case or regular case is infinite to the 1 solution. Okay? So I can, again, pay attention, I can realize an infinite number of orientation, because how many orientation are there between this and this? There are infinite, but not all, because it's a continuum, but limited. I cannot reach this point pointing in this direction, for instance. Okay? Now there are these exceptions to the previous case. Those are all regular. If we later on will compute the Jacobian in any of this configuration, we will find a full rank matrix. Okay? Now, if we stretch the arm, well, this is easy. How many inverse solutions are there? Only 1 solution. Okay? Which is 0 for the second joint, 0 for the third joints, and then some angle for the first joint, depending if I have to be there or there or there. Okay? But there are infinite solutions because the first joint, there's only 1 solution, and this solution actually is singular. Okay? We will call it singular even because in this context it's different from the regular number of solutions, which is infinity to the 1. Okay? What else? Suppose that we are placed now, the end effector should be placed at the boundary of the secondary workspace. So on the boundary of this circle. Now look, there are infinite to the 1 solution, and you can see this like, I should draw it because, and 3 out of this infinity of solution are singular. So something strange happens there. So I'm saying that, for instance, I need to be at this distance, which is L from the base. So I can start going here, then going there, and then going back. Okay? And now I let the first link move along a circle of radius L, and then I can put the second link like this and the third link like this. And you see that this is like a parallelogram moving like this. So I can open the parallelogram, then fold it, reopen it, and then fold it again. And by doing this, I'm realizing any orientation for the end effector. In fact, I'm at the boundary, so still included, of the secondary workspace. So there are infinite number of solutions. But there are 3 special of this infinite number of solutions, which are singular. And in fact, if all 3 links are in practice aligned, so folded or stretched along the same direction, like the first situation, then the robot loses some mobility. Okay? This is why these are called singular. Again, we'll be more accurate when we introduce the Jacobian associated to this robot. But if you think of this type of mechanism which was used in trains in the 2 centuries ago, of course this solution is singular because at this point you don't know if you're moving on this direction or in this direction. And the motion has a kind of a branch from this singularity. Okay? While if you are in this configuration, then you know that you can move either here or there, but they are two close motion. These are motion that diverge from each other. These are close motion in any case. This is just an intuitive explanation. Finally, pay attention. If you are inside, strictly inside the secondary workspace, so this norm is strictly less than L, then again you have an infinite number of solutions, and all of them are regular. So when you're close enough to the base of this planar 3R robot, no matter what you do, you can go everywhere with your end effector. This it means that you're regular. So you see that even in this apparently simple case, you have so many options that this suggests us to leave this argument right now, and just to summarize things of the general cases. So if the number of task variable is equal to the number of joints, now I'm using the generalized terminology for the inverse kinematic, then these are the possible situations. Either you don't have solution. Why? Because you're out of the workspace. Or you have a finite number of solutions, and this is the so-called regular or generic case. Or you have degenerate solution or singularities, which means that the number of solutions is different from those found in the regular case. So either a reduced finite number or an infinite number of solutions. Okay? So imagine that this is the 6x6 case. So the position and orientation for the end effector, and a robot with 6 joints, non-planar. If you have redundancy for the particular task, remember that this robot, a planar 3R robot, is redundant if I'm only interested in positioning of the end effector, because then the task is two-dimensional and I have 3 degrees of freedom in the structure. But if I would like also to impose the orientation, then I have strictly enough degrees of freedom for doing this. So it's m equal n. Okay. So if n is strictly less than n, and then we will say that the robot is redundant, again, what are the possible cases? Similar, but slightly different. No solution, because I'm out of the workspace. Or in the generic case, there are infinite to the n minus m solution. In the previous case, infinite to the 1, because I had n equal 3 joints, and the task was just positioning the end effector, which is m equal 2. Okay, so this is the generic case, an infinite number of solutions. And the singular case is when sometimes you have infinite number of solutions, or you have a finite number of solutions. For instance, when I'm stretching the planar 3R arm at the boundary of the primary workspace. Okay, this is all that it is, and when and here is just a short video of animation of the former Dexter robot arm, which was 8 degrees of freedom all revolute joint arm, the one that was used also for those application in the domestic domain for aiding less able people and so on, so the project MOVE8. So this video shows that if you're fixing position and orientation of the end effector, you still have an internal motion of all 8 joints, by the way, such that this is kept fixed, which means that if I'm assigning you this pose for the end effector, a task of dimension 6, and I have 8 joints, I have an infinity to the 2 possible configuration realizing the same position. So the original question that we showed with this colorful slide with the KUKA arm says, okay, I have this configuration, I have this pose. If I give this pose, how many solutions I have in the joint space? Well, in this case, I have infinite to the 2 solutions. And now this video just shows how to explore some of them. Okay? So, I think this is enough for today. We will continue this on Monday. Have a nice weekend.